Now that we know how to assign oxidation states to carbon, let's look at some organic redox reactions. And remember these definitions from general chemistry. Oxidation involves an increase in the oxidation state, and reduction involves a decrease or a reduction in the oxidation state. You might also remember that loss of electrons is oxidation and gain of electrons is reduction. So Leo the lion goes grr is a good way to remember that. Let's look at this starting compound here in this reaction, and let's figure out whether the starting compound has been oxidized, reduced, or neither. If you look at these three carbons on the left and these three carbons on the right, there's no change to those carbons, so there should be no change in the oxidation states of those carbons. But when you look at this carbon right here, the one I just marked in yellow, right, on the left it's bonded to, let me go ahead and draw that out, it's double bonded to an oxygen, and on the right it's bonded to a hydrogen, and on the left it's bonded to a carbon. But on the right here, that same carbon, right, is now bonded to an oxygen on the right. So it's still double bonded to an oxygen and has a bond to a carbon on the left, but on the right now it has a bond to an OH. So that carbon has likely changed its oxidation state, and we can go ahead and find the oxidation state using what we learned in the last video. So remember, you need to put in your bonding electrons. So let's put in our bonding electrons here. Each bond consists of 2 electrons. All right, so we know that when we're doing oxidation states, we need to think about electronegativity differences. And carbon is more electronegative than hydrogen, so we assign both of those electrons to carbon. Oxygen is more electronegative than carbon, so oxygen takes all 4 of those electrons. And when we get to carbon versus carbon, we can assume that those carbons have the same electronegativities, and therefore, for 2 electrons, we're going to split those 2 electrons up. We're going to give 1 electron to one carbon and the other electron to the other carbon. So this carbon is surrounded by 3 electrons, and we know carbon is supposed to have a number of 4 valence electrons around it. So carbon is supposed to have 4. In our dot structure here, carbon only has 3. Let me highlight them. 1, 2, and 3. So 4 minus 3 gives us plus 1, which is the oxidation state for this carbon. So this carbon right here has an oxidation state of plus 1 on the left. What about on the right? Let's go ahead and put in our bonding electrons, right? So we know that each bond consists of 2 electrons. Let me put those in here. And again, we think about electronegativity. This time on the right, this carbon is bonded to an oxygen now, so carbon loses those 2 electrons to oxygen, right? Oxygen is more electronegative. This top oxygen takes those 4 electrons, and again we split these 2 electrons. So this time carbon is only surrounded by 1. So to find carbon's oxidation state, we know that carbon's supposed to have 4 valence electrons, and from that we subtract the number of valence electrons around carbon once we've accounted for electronegativity, and that's only 1 electron now. So 4 minus 1 gives us an oxidation state of plus 3. So on the right, this same carbon now has an oxidation state of plus 3. So what happened in this reaction? Carbon went from an oxidation state of plus 1 to an oxidation state of plus 3. An increase in the oxidation state is oxidation. So our starting compound was oxidized here. So our starting compound was oxidized. In order for this to be oxidized, we would need some sort of oxidizing agent. So I'll write that down here really quickly. We would need an oxidizing agent to accomplish this reaction. And it's the oxidizing agent that itself is being reduced, because remember, whenever something is oxidized, something else has to be reduced. Let's think about the other definitions for the other definition, I should say, for oxidation. We know that oxidation involves the loss of electrons. So let's look at that here. On the left, right, carbon had 3 electrons around it, and when we added a bond to oxygen, right, carbon lost these 2 electrons. Over here it had those 2 electrons, on the left it had those 2 electrons, on the right it lost those 2 electrons. So now it's only surrounded by 1, and we see an increase in the oxidation state. So it's like carbon lost electrons. Also, there's a shortcut that you can use For this reaction, let's think about what that shortcut would be. I'll use red still. On the left, this carbon with an oxidation state of +1 has 2 bonds to oxygen. Let me go ahead and highlight them here. So here's one bond and here's the other bond. On the right, that same carbon now has 3 bonds to oxygen. So here's one bond, here's 2 bonds, and then this bond over here. So we've increased in the number of bonds to oxygen. And that can tell us we have an oxidation really quickly without going through and doing all these oxidation states. Notice we lost a bond to hydrogen, right? So over here we lost this bond to hydrogen, and we replaced it with a bond to oxygen. So an increase in the number of bonds to oxygen or a decrease in the number of bonds to hydrogen can tell you that your carbon is oxidized too. Let's do another one. So our goal is to figure out whether this starting compound has been oxidized, reduced, or neither. So again, these 3 carbons on the left, right, are the same as these 3 carbons on the right, and there's no change in those carbons, so therefore we would expect no change in the oxidation state. Same with this carbon. So we're going to focus in on this carbon. So on the left, that carbon has a double bond to oxygen, so we draw that in there, and then it's bonded to a carbon on the left and a carbon on the right. In our product, that same carbon is now bonded to only one oxygen. Let me go ahead and do that. Only one bond, I should say, to oxygen, and it's still bonded to a carbon on the left and still bonded to a carbon on the right. And it must have a bond to hydrogen in here, right? It's not drawn in, but it's assumed that you know that. So let's put in that bond to hydrogen, and let's find our oxidation states. So we start on the left and we draw in our bonding electrons, and next we think about electronegativity differences. So we know that oxygen's more electronegative than carbon, so oxygen takes those 4 electrons. Over here, right, we assume that the electronegativities for these carbons are the same, and so we split up those 2 electrons. We give 1 electron to one carbon and 1 electron to the other carbon. And same over here. So the oxidation state for carbon would be 4 valence electrons minus this. In this case, we have 2 around carbon, so here's 2. 4 minus 2 gives us an oxidation state of +2. So on the left, this carbon has an oxidation state of +2. What about on the right? Let's put in our bonding electrons, and again, once we've done that, we think about electronegativity, and we can assign an oxidation state to that carbon. So we know that oxygen is more electronegative, so oxygen takes those 2 electrons. Right? Again, we assume that these carbons have the same electronegativity, so we split up those electrons, we split up these electrons, but now carbon is bonded to hydrogen. So carbon is a little bit more electronegative than hydrogen, so we just give both of those electrons to carbon. And now let's find our oxidation state. We know carbon is supposed to have 4 valence electrons around it, and in our drawing here, once we've accounted for electronegativity, carbon is surrounded by 1, 2, 3, and 4. So 4 minus 4 is equal to 0. And so this carbon now has an oxidation state of 0. So that carbon went from an oxidation state of +2 to an oxidation state of 0. That's a decrease in the oxidation state. So carbon was reduced. So in this reaction, our starting compound was reduced. Right, so our starting compound was reduced, which means we would need some sort of reducing agent to accomplish this reaction. And it's the reducing agent that would be oxidized, because if something is reduced, something else has to be oxidized. We could also think about our other definition for reduction. Gain of electrons is reduction. And then let's look at what happened here. So the electrons that were gained, right, were these 2 electrons right here, because on the left we had this carbon with a double bond to this oxygen. On the right we have only now 1 bond to oxygen, right? So we gained these 2 electrons because we increased the number of bonds to hydrogen. So our other shortcut is to look at the number of bonds to oxygen, like we talked about in the last example. On the left, carbon has a double bond to oxygen, so 2 bonds to oxygen. On the right, we have only 1 bond to oxygen, so we decreased in the number of bonds to oxygen, so that's a reduction. Again, a fast way of figuring it out. Or we increased in number of bonds to hydrogen. Let's do one more of these problems. So our goal is to figure out if our starting compound on the left has been oxidized, reduced, or neither. And this time, these are the two carbons that we are going to analyze. Those are the two carbons that have changed in this reaction. So on the left, let's draw out what we have. We have a carbon with a double bond to another carbon, and both of those carbons are directly bonded to two more carbons. On the right, those carbons now only have a single bond between them, and this carbon on the left is bonded to a hydrogen, this carbon on the right is directly bonded to an oxygen, and let's put in those other carbons, right? We have another carbon-carbon bond, right? Let's put in those carbon-carbon bonds like that. Let's assign our oxidation states. So we draw in our bonding electrons, and we think about electronegativity differences, but we're going to assume once again that our carbons have the same electronegativity on the left. And so when we're assigning electrons, let's just pick one of those carbons. So let's pick the carbon on the left, right? We divide up those two electrons in that bond, give one electron to one carbon, one electron to the other. We do the same thing here. And for the double bond with 4 electrons, we divide up those 4 electrons. We give 2 electrons to each carbon. And so carbon is supposed to have 4 valence electrons, and around it, this carbon has 1, 2, 3, and 4. So 4 minus 4 is an oxidation state of 0. So this carbon has an oxidation state of 0. Same thing for the carbon on the right side of the double bond, right? It's in the same situation, so it also has an oxidation state of 0. What about for our product, right? Let's examine those two carbons. Let's put in our bonding electrons. So we draw in our bonding electrons here. So we put those in, a lot more bonding electrons to draw. And we think about electronegativity differences, right? Things have changed. So now let's focus in on the carbon on the left. So the carbon on the left is now bonded to a hydrogen, and carbon is a little bit more electronegative. So we give both of those electrons to carbon. And then we have carbon bonded to carbon, carbon bonded to carbon, and carbon bonded to carbon. So what's the oxidation state of that carbon on the left now? Carbon is supposed to have 4 valence electrons, and how many do we have around it? Let's see, 1, 2, 3, 4, 5. So 4 minus 5 gives us an oxidation state of -1. So this carbon on the left now has an oxidation state of -1. What about the carbon on the right? Well, we have a tie here, right? So we divide up those electrons, a tie here, but oxygen is more electronegative than carbon, so oxygen gets both of those electrons. So the carbon on the right should have an oxidation state of 4 minus 3. Here are the 3 electrons around carbon once we've accounted for electronegativity. So that's an oxidation state of +1. So this carbon has an oxidation state of +1. So overall, what happened here? Well, let me use red. So the carbon on the left went from an oxidation state of 0 to an oxidation state of -1. That is a decrease in the oxidation state. So that carbon was reduced. What about the carbon on the right side of the double bond that we started off with? It started off with an oxidation state of 0, and it went to an oxidation state of +1. That's an increase in the oxidation state. So that carbon was oxidized. What can we say about the starting compound overall? Well, the starting compound overall, there's no net change in the oxidation states, right? So on the left, for those two carbons, we had a total of 0. On the right, we had -1 and +1 for a total of 0. There's no net change. So this would be neither. The starting compound was overall, it wasn't oxidized or reduced. It's neither.